Hi everyone, this is the talk of PrimePar, efficient spatial-temporal tensor partitioning for large transformer model training. In pursuit of better model performance, LM training scales up in training dataset size and model parameter size, making LM training becoming increasingly expensive. Current prevalent LM training technique is 3D parallelism, including data, model, and pipeline parallelism, where data and model parallelism can be represented by tensor partition. However, the state-of-the-art LM training systems exploit limited tensor partition space, inducing inefficiencies of expensive collective communication and tensor replication. This work addresses these inefficiencies by investigating better tensor partition solutions. Existing tensor partition distributes suboperators along spatial dimensions. When two suboperators generate partial sum results, they require or reduce across devices. When they share some common tensor, this tensor is replicated across devices. From the perspective of suboperators, they don't necessarily induce or reduce or tensor replication in these two scenarios. In fact, distributing them along temporal dimension avoid both of these inefficiencies. This motivation led us to explore spatial temporal distribution of suboperators. Here we introduce some notations. The spatial index D is a binary vector denoting different devices. The temporal index T denotes the relative mapping time of suboperators partitioned from one operator. Thus, each suboperator is indexed by dt, indicating the suboperator runs on device D at time t. Each dimension of an operator has a dimension slice index, which is a function of d and t, indicating which slice of the dimension that suboperator dt holds. Existing spatial tensor partition can be seen as a sequence of elementary spatial partitions. Each elementary spatial partition selects one dimension to partition, and multiple such partitions are performed recursively. In this example, we first partition dimension n, and then partition dimension k. After these two recursive partitions, the original operator is partitioned into four suboperators, each distributed to a separate device for parallel execution. We observe the essence of inefficiencies of spatial tensor partitions from the DSI perspective. Firstly, examine the DSI In of dimension n, which is the summed over dimension of matrix multiplication. Here, In can't take value 1 for devices with D1 equals 0 and vice versa. This means each device doesn't have access to all slices of dimension n. Thus, all reduce is necessary. All reduce happen between devices with different D1. Secondly, examine the DSI tuple IN. Since it only varies with D1, it takes the same value for devices that have the same D1 but different D2, inducing the replication of tensor with dimension m and n. In fact, the sources of inefficiencies denoted by bullet points 1 and 2 are inevitable when you only consider spatial tensor partition. Inspired by Cannon matrix multiplication, we consider spatial temporal DSIs. In this set of DSIs, you can see that In varies with temporal index t and takes all possible values as t varies. This ensures that for an arbitrary device, during its process of computation, it can have access to all slices of dimension n to compute all partial results and accumulate locally. What's more, at given time t, the DSI tuple of any tensor is different for different devices. Based on these insights, we introduce a novel spatial temporal tensor partition primitive. When designing this primitive, we obey three design principles. First of all, it should be collective communication free. We achieve this by letting DSIs of summed over dimensions varied with t to take all possible slices across time. Secondly, we avoid tensor replication by ensuring that for any tensor, its DSI tuple can't take the same value under the same t and different RC. Thirdly, we ensure the continuity of tensor distribution between different training phases. For example, the weight tensor is utilized in both forward and backward phases. Thus, we design DSIs to align the weight distribution between the last step of forward and the first step of backward. Let's look in details by examining the example of k equals 2 for the first step of forward. The initial tensor distribution of OIW can be computed via evaluating forward DSIs with t equals 0. We determine the communication pattern by checking which device back at time t was holding the part of tensor that device RC needs at time t plus 1. As for tensor I, its DSIs match when evaluating RC plus 1t and RCt plus 1, which means each device should receive I from its right neighbor. Note that for the rightmost device, for example, device 03, its right neighbor is device 00. Applying similar reasoning to tensor W, we determine that each device should receive W from its bottom neighbor. These communications follow a cyclic ring pattern, which are point-to-point and not data-dependent on the computation results. Thus, they can be overlapped with computation by utilizing double buffering for tensors I and W. Forward step 1 and 2 follow the same scheme as step 0. Under this scheme, each device computes and accumulates a partial sum for its part of output at each step. After all steps, each device obtains the total sum for its part of output. Note that no communication is required in the last step of forward, because only tensor W is used in both forward and backward, and we designed DSIs so that W distribution in the last step of forward match that in the first step of backward. For the backward phase, evaluating backward DSIs of tensor W shows that each device should receive W from its right top neighbor. Thus, the communication pattern of W consists of oblique cyclic rings, where different rings are labeled with different colors. One oblique ring may not appear continuous. For example, the right top neighbor of device 02 is device 33. Although the communication directions are different from forward, these communications are also point-to-point and can be overlapped with computation. Backward step 1, 2 follow the same scheme as backward step 0. The situation for the last step of backward is kind of special. After completing training a batch, the tensor W should revert to its initial distribution in the first step of forward. We adjust W distribution in the last step of backward. Evaluating DSIs of the last and first steps of backward and forward for W shows that a leftward shift is required. Also, we have designed the DSIs so that the tensor DO and I can be directly used when entering gradient phase without other communications. Communication patterns during gradient phase can be determined with similar reasoning. The only special thing that worth noting here is that we add the delta term to gradient DSIs of IN and IK, so that the dW distribution at the end of gradient is aligned with the W distribution at the first step of forward. The impact of this delta term on communication is to add a leftward displacement to the communication directions in the penultimate step of gradient. The delta term also results in the leftward shift of the final step's dW distribution compared to previous steps. In the final step, compute while shifting previously accumulated dW leftward. After that, add the final step of computation result with shifted dw. In this way, each device computes the final dw with its distribution aligned with initial distribution of w. The key aspect of the cost model is modeling the intra- and inter-operator communication latency. Intra-operator communications happen in groups, where the grouping pattern is determined by the partition strategy. For example, the R-reduce during forward of a linear operator is induced by partitioning dimension n. To determine its grouping pattern, we only need to check partitioning dimension n happens at which positions in the partition sequence. On the left-hand side, the positions correspond to spatial indices D1 and D3. Thus, each R-reduced group consists of devices that differ only in D1 and D3. We model the latency as linear function of communication size. The grouping pattern determines the interconnection topology and bandwidth within each group. Thus, we profile separate linear coefficients for each grouping pattern. The number of grouping patterns is not greater than the number of devices, making our profiling practical. For two consecutive operators N1 and N2, due to different partition strategies of N1 and N2, the distribution of N1 output generally doesn't match with that of N2 input. For each device, there may be some part of N2 input that is not locally available when finishing the N1 computation, which requires communication. By evaluating DSIs of N1 output and N2 input, we can determine the length of intersection in each dimension to compute the communication size. We model the inter-operator communication latency as a linear function of the total communication size. The overall cost is the sum of all intra- and inter-operator costs. We aim to minimize this overall cost. However, the search space size is the product of tensor partition space sizes of all operators. This is a complex combinatorial optimization problem requiring efficient optimization algorithm. Dynamic programming breaks the complicated problem into easier subproblems in a recursive manner. However, in our scenario, naive dynamic programming is still too complicated. Specifically, one operator's partition state should be kept in the optimal substructure until the iteration reaches the furthest target operator of its outgoing edges. The complexity grows exponentially with the number of operators whose partition state are kept in the optimal substructure. To solve this, we utilize segmented dynamic programming. The segments were selected such that within each segment, at most two operators' partition states need to be kept in the optimal substructure, namely the first operator and the operator at the current iteration step. Optimal substructure of segments can be tractably merged to compute larger scope substructures. For transformer model structure, each transformer layer only need to be partitioned into 3 segments. The optimal substructure of a whole layer is computed by 2 merges. Since transformer models consist of repeated layers, we only need to compute optimal substructure of a layer once and merge layers to complete the optimization of the whole model. We evaluate training throughput and peak memory occupancy of several transformer models. Compared to baseline, PrimePar brings speed up and memory saving simultaneously, and the improvements are more significant when scaling larger models to more GPUs. From the latency breakdown, you can see that collective communication latency is significantly reduced. Although extra ring point-to-point communications are introduced, these communications incur small latency and can be fully overlapped with computation latency. You can see that computation latency remains the same as baseline. This indicates that with better utilization of communication resources, PrimePar doesn't compromise the efficiency of computation. Here, we compare the kernel execution timelines of one MLP block when parallelizing to 8 GPUs. Benefiting from the application of spatial-temporal tensor partition primitive, PrimePar has significantly shorter communication kernels. Using PrimePar in 3D parallelism also speeds up training. Note that larger models with 3D parallelism offer PrimePar more optimization opportunities, as they prefer configurations with higher degree of model parallelism. In conclusion, PrimePar explores the spatial-temporal tensor partition space and finds novel partition primitives that are communication efficient and provide possibilities to better utilize hardware resources. We provide an insightful formulation of spatial-temporal suboperator distribution, by which it's convenient to analyze communication patterns. As a final remark, we have only designed one primitive out of the spatial-temporal tensor partition space, and we think further explorations is worthwhile. Thank you for your listening.